Hi, we are research team from National Yangming Jiaotong University and MediaTek Incorporated. Today, we are going to introduce our work. Best of both worlds, learning arbitrary-scale blind super-resolution while dual degradation representations and cycle consistency. Single-image super-resolution, SISR, is a widely studied research problem which aims to construct a high-resolution image, HR, from a low-resolution image, LR. Despite the magic leap brought by the recent deep neural network, it is still considered to be quite challenging due to its ill-posed nature. To this end, two branches of SISR methods have emerged, which are blind super-resolution, blind SR, and arbitrary-scale super-resolution, ASSR. Blind super-resolution aims to reconstruct SR image under the unknown degradation. However, the SR methods in this category handle only specific scale. ASSR allows generating arbitrary-scale blind SR image with only one model. But the related works, now they only assume the LR image are under specific degradation. In this work, we propose to tackle both blind SR and ASSR at the same time, which is the first of its kind of our knowledge. We first take a look at the general means of both methods. Blind SR can be categorized into two groups by the way of estimating the prior information of kernel. The first one is to explicitly estimate a physical kernel. It is meaningful, but it may suffer from kernel mismatch problem. The second one is to implicitly predict a lantern representation of kernel. It alleviates kernel mismatch issue, but how to ensure the discriminative among various degradations would be other concerned issue. And the seminal works of ASSR is to learn to represent image as continuous function. Although it may seem intuitive to directly integrate of both methods, we argue that it is actually non-trivial. To integrate existing ASSR methods with explicit kernel estimator, the ambiguity is introduced under different scales. For example, when applied the same kernel on the HR image, but downsample with different scales, the estimated kernel is mismatched to the real one. For integrating with implicit degradation predictor, the problem is that learning a discriminative representation is more complicated. To this end, we propose a holistic framework by solving affirmation issues and utilizing their strengths, also constructing a closed loop to benefit overall model training. Our full model consists of 3 modules. In upsampling process, it uses an implicit degradation predictor and adaptively works with arbitrary-scale super-resolution module, which generates the SR with the size of HR. Moreover, in downsampling process, the explicit kernel estimator is used to estimate the kernel in LR space and convolve with the SR results. The upsampling and downsampling together form a closed loop which allows us to drive the model optimization. Let's look at more details of our structure. For implicit degradation predictor, we wonder how to learn better representation. The insight is that high-frequency parts are typically suppressed during blurring and downscaling, which results in different levels of degradation in different frequency bands for the same image. Therefore, we project the LR image with wavelet transform and use only high-frequency subbands. And contrastive learning is adapted to learning degradation representation. For arbitrary-scale super-resolution module, image feature extractor is adaptive to the implicit degradation. That is, the coefficients in residual blocks are adaptively transformed from the degradation, which helps us generate better arbitrary-scale blind SR image. And for the explicit kernel estimator, we design a lightweight deep linear convolution structure, which uses implicit degradation as input rather than a whole LR image. Furthermore, we estimate the kernel in LR space instead of HR space. So there is no ambiguity with respect to different scales. To supervise training the LR kernel, we can derive the ground truth kernel from the Fourier transform. Lastly, we leverage the inherited strength of ASSR to achieve downsampling instead of adopting separate downsampling module or relying on bicubic downsampling. The generated SR with size of LR then convolved with the estimated kernel in LR space. This is our full model, and we train the whole model in 2 stages. First, train with both degradation modules to improve the representation power of degradation. Then super-resolution module is optimized. During inference, we only require the implicit degradation predictor and the arbitrary-scale super-resolution module to achieve arbitrary-scale blind SR results. This is one of our demonstrative results. Our method outperforms all the baselines on both integer and continuous scales. Also, it demonstrates sharp edges, preserve better structure, and less distortion. For more information, please visit our section and paper. Many thanks for your attention.